Okay, so in this lecture we are going to look at some immediate consequences of the definition of a linear vector space. Right? So we defined what a linear vector space was in the previous lecture, and some of these properties will immediately give us some constraints. Right? That's what we are going to look at in this lecture. Okay, so we said that a linear vector space is a set of these abstract vectors and it must satisfy certain properties. One is closure under vector addition, then there is closure under scalar multiplication. So then we also said that it has a null vector, right? So now we want to argue that it automatically implies that this is going to be a unique null vector, right? So the definition does not by itself explicitly, it does not have to forbid the presence of more than one null vector, but we will see that it's impossible for you to have more than one null vector. There is going to be one null vector. You can actually prove it, right? So many a time you will see in textbooks where this is taken to be a requirement, right? So that there is a unique null vector itself is part of the definition, but it's actually, we just want to point out that it's not essential to encode it into the axioms. It's something that can be derived, right? So how does this come about, right? So you have suppose there exists a second null vector 0 prime, right? So that this is the argument. So let's concentrate on so why there is a unique null vector. Suppose there is a second null vector 0 prime, then since 0 prime is an element of S, so the property of a null vector is that if you add x to 0 you must get back x. So now 0 prime is an element of S and 0 is a null vector, so 0 prime plus 0 must be equal to 0 prime, right? So 0 prime is this vector from this space and it has remained unchanged when you have added the null vector to it. But on the other hand, 0 itself is an element of this vector space and 0 prime is a null vector. So if you add the null vector to any element of this space 0 plus 0 prime, you must get back the same vector that you started with, which is 0. So thus, since addition is commutative, right? So 0 is equal to 0 plus 0 prime, which we have just showed here, and whether it's 0 plus 0 prime or 0 prime plus 0 prime, 0 prime plus 0, which is given to be this 0 prime, it's the same, and therefore 0 equal to 0 prime, right? So it just follows from commutativity that you cannot have more than one null vector. There is a unique null vector in your vector space, and likewise you can argue that the additive inverse of any vector is also unique, right? So we have said that every vector of your vector space has an additive inverse, and that now we are going to say that we don't have to explicitly specify that it's unique, but it has to be unique. It follows from the structure of all these properties already. Suppose, okay, so what is the proof for this? Suppose there exists two inverses, let's say x inverse and x inverse prime, I'm going to call them. So for a given vector x, there are two additive inverses, x inverse and x inverse prime. So x plus x inverse must be equal to 0 by definition of the additive inverse. So let us add this x inverse prime to both sides. So I'm going to add from the left side. It doesn't matter because the addition is commutative, but so let's say I add from the left side, and then I will use associativity of addition. So I have x inverse prime plus x inverse is equal to x inverse prime plus 0, right? So because on the right hand side also I have added x inverse prime. But what is x inverse prime plus x? I can combine the first two objects. So but this is going to be x inverse prime plus x also must be 0, right? This is by definition. I have said x inverse prime is an additive inverse of x. So x inverse prime plus x must be equal to 0. So we immediately have the result x inverse is equal to x inverse prime. So the inverse is unique and it is customary to simply write the inverse as minus of this vector, right? So you can sometimes the minus sign is put inside the ket, but it's simplest to just write it as minus the vector x, and then you explicitly see that the addition of x plus minus x is equal to 0. So the vector 0, right? I mean, if you want to be very precise, it must be written as x plus additive inverse is equal to the vector 0, right? It's a vector 0, but oftentimes it is just written as equal to 0, right? Just the scalar 0. And so the reason for this is the following. So we will show one more consequence of this. So you can show that if you multiply any vector 0 with any vector x with the coefficient 0, you're going to get the vector 0. So in some sense, so the analogy is with 2D vectors. If you take a vector and multiply it with the scalar 0, you're going to annihilate any notion of direction with it, right? It's the same whether if you multiply a vector which is pointing along the x-axis by 0, or whether you multiply a vector which is pointing along a direction 45 degrees to the x-axis with 0, you're going to just get a 0, right? So, but it should, I mean, technically speaking, it is 0 with the x component is 0 and the y component is 0, but it's we would usually just write this down as 0. The null vector 0 is often just written as the scalar 0, and you have to understand from the context that that's what is being referred to. Okay, so let's prove this. So we can prove, so we had this condition, we wrote down explicitly one property of scalar multiplication, which is that if you multiply any vector with the scalar 1, you're going to get back the same vector. So sometimes this property is also sort of encoded into the properties of addition, multiplication of vectors, but this also is something that we can prove directly from the distributive law. So why not keep the basic set of requirements or axioms as minimal as possible, right? So let's give out this proof. So the idea here is to show you how some of these abstract proofs work out, right? So the properties of multiplication and the distribution law with respect to addition of scalars, we have, if you take any vector x is equal to 1 times x, so this is part of the rule that is already given to us. It's part of the properties of scalar multiplication. But what is 1? 1 is the same as 1 plus 0, right? This is the addition of scalars, 1 plus 0. And then we have this distributive law, 1 plus 0 times x is the same as 1 times x plus 0 times x, and then which is the same as, again we use this rule that 1 times the vector x is equal to x, which is equal to, and then you have plus 0 times x. So now what we have managed to show is any vector x is the same as the vector x plus 0 times vector x. Now we can add this additive inverse on both sides, vector x added to its additive inverse on both sides, from the left side if you wish, it doesn't matter the order because this operation is commutative. You will get a cancellation, right? X minus x will give you the vector 0, the null vector 0, and we immediately have the result 0 times x is equal to vector 0, right? So you might think that why are we are working very hard to prove things which seem totally obvious, right? So the objective here is to show you how it's like an exercise in rigor, how you can start with some very small set of axioms and then work out proofs of statements which look obvious, but the point is to show you that even these kinds of assertions can be proved based on some very, very elementary set of axioms, right? I mean, the whole course we are not going to take this approach, right? So we have a physicist proof approach to a number of problems that we'll encounter as we go along, but these are simple to understand, and they have their own beauty, and that's why we are including some of these arguments right at the beginning. So we show with the help of some very basic set of definitions which go into what a vector is and what a vector space is, we can show that there is this inbuilt constraints which make both the null vector and the additive inverse of these vectors unique, and also this property of 0 times x is equal to the null vector 0 also comes out. Thank you.